Welcome back to this course on blockchain and its applications. So, in the last class, we are talking about the idea of cryptocurrency, and we have seen that to have a cryptocurrency in a complete distributed environment, you need a consensus mechanism. So, we stopped at this point that whether we can use the vast literature from the distributed consensus mechanism to actually apply them in the context of cryptocurrencies or not. So, today we are going to see that, and we'll see that how this particular idea or this particular question in the cryptographer community raised the butt of this popular cryptocurrency named Bitcoin. So, let us carry forward our today's lecture. So, the topics that we are going to cover in today's class is this concept of consensus over an open network, followed by the idea of Bitcoin, and finally a discussion on the Bitcoin as a cryptocurrency, as a kind of most popular, possibly the most popular cryptocurrency. So, these are the keywords for today: Bitcoin, open consensus, and an idea which we name as the proof of work or POW, that we are going to see in brief. So, this is the point where we stopped in the last lecture, that to understand that every financial transaction is correct, I need a way to verify that the person who has initiated the transaction or the person who has put up the transactions in a common media, in a common platform, that person has solved certain puzzle. Well, so how to solve that puzzle, what that puzzle is, that we are going to look later on. And for this particular case, what I need, that I need a kind of consensus among the participants, others to observe, others to see that whether this particular transaction is valid or not, and from that perspective I need a kind of consensus mechanism in the distributed system, in a distributed system. Now, we stopped it by asking this question that, well, can I use the classical distributed system literature to apply the consensus algorithms that have been proposed or that have been utilized in that context of distributed system. So, one of the major requirement for cryptocurrencies is that the network is open. Well, so what is meant by an open network? So, an open network basically means that anyone can join or anyone can participate in the network. So, if you just try to remember, or if you try to remind our initial objective of developing a cryptocurrency, our objective was that, well, anyone should be able to use that cryptocurrency to do financial transaction, and I want my entire network free from any kind of central authority like a bank or like a government. But at the same time, I want to ensure that all the financial transactions which are happening on this cryptocurrency, they are legitimate, they are valid. Well, now if you just try to think of it, it is a very challenging problem. Why it is a challenging problem? Because first of all, I am saying that I do not want involvement of any bank or any government. Now, if I do not want the involvement of any bank or any government, then immediately the question comes that who is going to monitor that the transactions which have been originated or the participants who are performing certain financial transactions, those financial transactions are correct. Well, and for that purpose, as I mentioned earlier, we need consensus. But again, the challenge here is that my network is open. So, that means the millions of people who are there in the world, any two of them can initiate any transactions at any point of time. Well, so I cannot say that, well, to use that cryptocurrency you need to first register somewhere and then you need to come to and participate and join in this cryptocurrency network. That I cannot do. Why I cannot do that? Because if I do that, that will violate my basic principle, or that will violate my basic design goal. Well, because I want a kind of complete open marketplace where anyone should be able to do the financial transactions. Now, this poses a challenge here. Why that is a challenge? Now, let us try to revisit the distributed consensus algorithm that we had discussed earlier in the context of the distributed system literature. Now, how that distributed consensus works, if you remember? So, we are taking or we are discussing again that example of burger and pizza. So, what happened that whatever be your choice, you are making a phone call to your friends saying that, hey, I like pizza. Well, or if you want to go for a burger, you say that, hey, I prefer burger, I want to go for a burger. So, that way everyone gets the vote for all of the friends and finally count the majority. Well, so that was my algorithm. But to run this algorithm, the primary point that you have is that you need to make a phone call to your friend. Well, so that means the algorithm is based on message passing. Well, and to do the message passing, you need the identity of others. So, unless you know that who are the friends, you cannot make a phone call. Well, so for example, if I say that, well, after this class today I am going to have an online party, and typically we do not know that who are the participants in this NPTEL lecture. So, I cannot make a phone call or I cannot send a message to all of you saying that, hey, we are going to do the party. Well, just assuming that I do not know who are going to attend in this NPTEL class. Well, although in practice I know that you have registered for the course. Well, just think of that this lecture has been put up in YouTube and people are watching this lecture. Well, so I do not know the identity of others. Well, so this poses the limitations here, that because of this particular reason, the classical distributed consensus algorithms, they work only within a closed system. So, when you know that who is the participant in the network and you want to reach to a consensus among those set of participants, then only you can use a classical distributed consensus mechanism that we have discussed in our earlier class. Well, but in contrast, here I have an open network. Now, the moment I have an open network, I cannot use message passing because I do not know the ID of all the participants, and because I do not know the identity of all the participants, this kind of message passing based algorithm does not work there. So, comes the question that how we are going to solve it. And in 2008, this pioneer white paper that got floated in the internet, the title of the paper is Bitcoin, a peer-to-peer electronic cash system, that was been written by someone called Satoshi Nakamoto. Well, and that paper or that white paper got public, it came in the internet. Well, and people got stunned. Why? Because this is the paper which has given an idea about how you can reach consensus in a open network by avoiding the idea of message passing. Well, and from that perspective, it had solved this consensus problem which is required to do the financial transactions on an open marketplace. Well, because again I am repeating, to do the financial transactions in an open marketplace, when you do not have any bank or any government to verify that you have done the transactions correctly, what you have to do? That transaction verification need to be done in a decentralized way, in a distributed way. Well, so from that perspective, I need a kind of distributed consensus protocol. But my basic philosophy of cryptocurrency says me that I cannot have a kind of closed marketplace, I cannot have a closed network. I do not know, or I will not be able to know the identity of all the participants who are joining in that network, and that is the reason I will not be able to run a message passing system. So, the question comes that how this particular paper which proposes this idea of Bitcoin, which claims that, well, in a peer-to-peer network, or rather in an open peer-to-peer network where the participants do not know each other, how you can reach consensus on the financial transactions. Well, so let us try to see this idea. So, whenever we see that, or whenever we tell that, well, I would like to have a consensus in an open network, so how can we achieve this? Well, so one of the idea can be that, well, what we can possibly do that in some way, if I can find out that well one of us becomes the leader and then that leader actually verifies the transactions and certify that well this transaction is valid transactions, you can add that transaction to your committed transaction list. Well, so this is the point that somehow I need to find out a leader. So, the question comes that how do I find out a leader when no one knows each other? Well, here comes this idea of puzzle solving. Well, so what we say that let the network elect a leader. Well, so the participants do not know each other, but what might happen that the network will run certain thing and based on that a leader will be automatically get elected. So, what is the idea? The idea is something like this. So, the network throws up a complex puzzle, well, asking everyone to solve it. Well, so it is something like that. I have thrown a puzzle to you, not only you. So, I have said that hey, this is a puzzle. Now, all of you should try to solve it simultaneously. So, the person who is going to find out a solution of that puzzle, I will consider that person as the leader and that person can directly connect to me and whatever that person will tell that whether that person wants to go for pizza or go for burger, we all will agree to that. Well, so this is the kind of protocol or this is the kind of constraint that I am posing here. Now, from here, well, so here comes the kind of interesting idea. So, what type of puzzle I have to give? Well, I have to give a really very difficult puzzle, because you see that here if I just throw a simple puzzle, then what might happen? That multiple people can solve the puzzle simultaneously. Now, when multiple people are solving the puzzle simultaneously, then my original objective got violated. At that case, I will not be having one leader, I will be having more than one leader, I will have multiple leaders. Well, again I need to run a consensus algorithm among those leaders to find out that what we are going to do, that I do not want. Well, now when I do not want that, I need to give a really hard puzzle, so that I know that well let people try to solve it for, and that I know that that will take time. It is not like that immediately people will be able to solve the puzzle. Well, so let people take their time, let people try to solve the puzzle, but eventually one will be able to solve the puzzle and say me the answer, and then I can choose that person as a leader, and whatever that person vote for, whether for burger or whether for pizza, all of us are going to agree to that. Well, but here comes an interesting primitive again, that the puzzle that I am going to throw, that puzzle, as I have mentioned, the puzzle need to be really hard, but at the same time I need to ensure that one person is going to solve the puzzle, and the person who is going to solve the puzzle becomes the leader, and the decision that the leader says, everyone agrees to that. Well, and as I have mentioned that the puzzle need to be very difficult. Well, so the question comes that what should be the other property for that puzzle? So, the other property of the puzzle should be, although it is difficult to solve the puzzle, but it should be easy to verify the puzzle. Because why that is so? Because whenever say this person has say solved the puzzle, and when this person has solved the puzzle, at that time others are going to verify whether this person has really solved the puzzle or not. Now, if this verification become complex, that does not mean anything. Well, so then again verification will take time. I do not want that. What I want, that solving the puzzle is complex, but verification is easy. So, this is going to be the property that the puzzle should solve. or the puzzle should support. Now, with that, what I can say that well, it is not a single round in which the puzzle is getting solved, rather different people can solve the puzzle at different round. Well, so it is like that, right. So, whenever you are throwing up a hard puzzle and then multiple hard puzzles, it is not like that a single person will be able to solve it all the time. Well, or the single person, the person who is solving the first, it is a single person all the time. Rather, different people will solve the puzzle at different round. So, that way in different round, different people will get elected, and whatever that person is saying for, I will go with that. So, maybe in today's lecture, one of my friend that solves the puzzle and that person says pizza, we go for pizza, and then tomorrow's lecture another person wins the puzzle, well, then that person may say burger, we go for the burger, and so on. Well, so that way everyone becomes happy, well, because at different round different people may get elected. So, as I have mentioned that to design a good puzzle, the puzzle should have this property that it should be difficult to solve, but easy to verify. Well, so this is particularly because to ensure that whenever someone is solving the puzzle, during that time this generation or solving the puzzle is difficult, to ensure that well, eventually one person solves the puzzle, but while doing that verification I want to ensure that people verify that puzzle in an easy way. Well, so that is the kind of property of a good puzzle, and as we have seen earlier, so you have already learned about that in earlier classes, that what can be a good puzzle? A good puzzle can be generated with the help of cryptographic hash function. How? Because you see that if I have a hash function like this, say y equal to h of say x append some nonce value, and if I say that well, y and x is given, well, and you need to find n. Now, you see if this is the requirement, this is my puzzle, then from the properties of the cryptographic hash function, I do not have a deterministic algorithm or a deterministic way to solve this particular challenge. Well, so what I have to do? I have to do a random search, try with different value of nonce, different value of n to find out a n which satisfies this. So, this is a challenging problem, this is a hard problem to solve. Well, people need to try with different numbers, and the person who has been able to find out the nonce or n first, that person wins the game and in that round. But once you have found out n, then you know x, you know n, computing the hash function is easy. So, you can easily verify that by computing y1 equal to h of x and the n value that you have computed, say I am writing it at n subscript c. So, you can easily verify whether y is equal to y1 or not. If y is equal to y1, that means the person who has claimed that hey, I have solved this puzzle, that person is correct. Well, so this is the idea which is being applied in the Bitcoin paper to elect a leader who is going to verify and add a set of valid transactions in a public ledger. So, as I have mentioned that y equal to h of x append n is a good puzzle. So, Bitcoin uses that idea. Well, and this particular consensus algorithm in Bitcoin, it is termed as proof of work. Well, why proof of work? Because you have done certain work to find out a solution, and that solution works like a proof that you have found out the solution. Well, so in this 2008 white paper that got floated in the internet, it actually combines this idea of hash chain, this puzzle solving as a proof. So, this puzzle solving as a proof, it was initially proposed in BitGold. So, the Bitcoin paper actually formalizes that idea, and then the idea of something called the coin mining in an open P2P setup, in an open peer to peer network. The idea of coin mining we are going to discuss later on. So, it combines all these ideas together and finally propose this cryptocurrency called Bitcoin. So, the consensus algorithm that is being proposed in this particular paper, as I mentioned earlier, it is named as proof of work or POW, and people also call it as the Nakamoto consensus. Well, now comes the question. So, you remember the FLP impossibility in the distributed system literature that we discussed earlier. So, the FLP impossibility says that in a pure asynchronous environment, you cannot support safety and liveness together. Well, and the classical distributed system algorithms, they had given priority to safety over liveness. Well, and that is why they rely on a kind of message passing architecture. So, the question comes that what pioneering thing this particular Bitcoin paper has done or Satoshi has proposed, which was actually helped to design a consensus algorithm in an open network. And the key to success here is that this Nakamoto consensus or proof of work, it had given more emphasis on liveness rather than safety. So, here it is a departure from the classical distributed consensus algorithm. So, whereas the classical distributed consensus algorithm, which are based on message passing, they had given more emphasis on safety compared to liveness. This particular proof of work algorithm, it gives more emphasis on liveness compared to safety. So, that basically means that the participants may agree on a transaction that is not the final one in the chain. Well, so this is important. So, it basically says that, well, we have possibly agreed on a transaction, but that transaction might not be final. What we have verified? We have verified that, well, that transaction is a correct transaction, but whether that transaction can be immediately executed or not, that we cannot say immediately. You need to wait for that to decide whether this transaction is a final transaction. So, for example, if I have the example that I had given you earlier, that say I have 100 rupees and in that 100 rupees I want to give 60 rupees to one of my friend, say friend A, and 80 rupees to another of my friend B. Now, these two transactions cannot happen, only one of them can happen. Well, so what might happen in case of such kind of proof of work based system, that, well, one person says that, well, you include 60 and you discard 80, another person may say that, hey, you include you include say 80 and you discard 60. Okay. So, such kind of things can happen. So, that way, although both agrees that, well, both of the transactions cannot be accepted simultaneously, we are going to accept only one of them, but which one of them, that we cannot tell immediately. Well, so that for that we need to go for multiple other routes and we need to find it out. And how we actually do that in the subsequent lectures, we are going to discuss that in details, we are going to cover that in details. Well, but from that perspective, so it says that, well, for the time being, let us take a decision that, well, we are going to consider only one of these two, okay, and the discard others, and now let us proceed further by checking with the next transaction, okay, the transaction for the from the next person. Well, and eventually out of these two transactions, one will get accepted. Well, so that way we say that, well, the transactions are not final on the chain immediately. So, with this concept, let us see that why this can happen. in the idea of puzzle solving that we have discussed earlier. Now, with that puzzle solving idea, whatever hard problem you throw to the participants, it is always possible that more than one participants are able to solve it. Although my expectation is that I have given a really very hard problem to the participants to solve it, and eventually only one person would be able to solve it, who would rather solve it for the first time. So, we are going to consider the person who is solving it first. So, only one person is going to solve it, but what we are going to ensure that or we cannot ensure that multiple people will not be able to solve it. It can always happen that multiple people are able to solve it, and if multiple people are able to solve it, we are in a dilemma. Well, so whether it is pizza or burger, we cannot say it immediately. So, in terms of financial transactions, the example that I have given, that well, we agree that we will choose either one of the two transactions, either the transactions to person A with 60 rupees or the transaction to person B with 80 rupees, but immediately I cannot say which of the two transactions I am going to consider. For that I need some more time, but that was not there in the classical distributed consensus algorithm. In case of classical distributed consensus algorithm, what had been decided, that had been decided immediately. Okay. So, that way they had something called a consensus finality. So, that consensus finality is not present in case of proof of work or the Nakamoto consensus, which designed the consensus algorithm for the open environment. So, considering the FLP impossibility that we had discussed earlier, so this classical distributed consensus algorithm, they gives more priority to safety, whereas this open consensus algorithm, the Nakamoto consensus, it gives more priority to liveness. Now, interestingly, this Bitcoin paper, it had not coined the term blockchain in the papers, it had used the term block and chain separately, but together that paper has never used the term blockchain. The term blockchain came later on. So, around 2011 this concept of Litecoin got introduced, that Litecoin was another lightweight cryptocurrency. Then in 2015 the Ethereum network went live. Ethereum is something which supports the development of decentralized applications or DApps. We are going to see later on that how it helps or what are the kind of DApps that we have. And sometime around 2016 this term blockchain got popular. Well, so from that 2016 2017, from that years people started talking about blockchains, and this idea become really very popular. Well, because people are able to find out multiple different applications of blockchain beyond cryptocurrencies that we are going to discuss in the next class. So, in conclusion, what we have seen today, that this classical distributed consensus algorithms, they can't be applied on the blockchain for cryptocurrencies, particularly because they are based on message passing. In an open network you cannot support message passing. So, in an open network we have used a different consensus mechanism, whereas the classical consensus mechanism, they gives more priority to safety over liveness. So, safety is more priority over liveness. In case of Bitcoin, it is just the opposite. So, liveness has been given more priority over safety, and that way it proposes an open consensus algorithm. But an important question that remains is that why should someone solve this puzzle? Why should someone be interested in solving the puzzle? Well, because you remember that the puzzle that I have shown, or the puzzle that have been given by the network, it is a kind of hard puzzle. Well, so you really need to invest your computing power to solve the puzzle. Well, so this is my next open question, that how I can attract people to solve this particular puzzle and participate in the Bitcoin network or my cryptocurrency network. So, in the next lecture we are going to discuss this in details. So, I hope that this broad idea of this puzzle solving for consensus is clear to you. Later on we are going to discuss this concept of puzzle solving and how the consensus are actually achieved in a proof of work based consensus algorithm. We are going to look into the details of that. This does give you a kind of broad overview about how the system works, and in the next class we are going to answer this question that how we can attract people to participate in a Bitcoin or a cryptocurrency network. So, that is all for today. Hope to see you in the next lecture. Thank you all for attending.